So we're looking at our problem where we've got a robot in a room, and it's kind of a nice square room, and we don't know where we're at. We just kind of got dropped down here. So that means each individual cell's an equal probability, or it's a uniform distribution. And let's look at some situations that have a little bit of uncertainty in them in terms of like our measurement of things. Because measurements are usually never 100% certain, right? There's always some, there should always be some doubt that your measurement was 100% right. So let's say this first. We don't know our robot's orientation, but let's say that we get plopped down, we don't know where we're at, and so we take a measurement to see how far away the nearest wall in front of the robot is. And it turns out that distance is 1 unit. So first, let's find all the cells. So this event we'll call wall 1 unit. So the wall's 1 unit away. So now we know that it couldn't be here because the wall would be 0 units away. So here the wall is 1 unit away. Same as here, here, and here. Couldn't be here because that means the wall would be 2 units away. And let's say that the way our sensor works, we're 90% certain that the wall is 1 unit away. So that means there's a 10%. It's kind of nice Excel does that. A 0.1%, or 0.1 probability that the wall is more than or less than 1 unit away. Basically saying there's a 10% chance that this is wrong. So let's now scale the way we kind of understand where we might be here. The first thing we need to do is sum up this zone for our positive space. So I'm going to take that. Get my denominator. So my denominator is 0.32. So that's what I'm going to divide everything by. So now I'm going to go equals the probability, the previous probability of that location times the probability of the event. Excuse me. So times 0.9, and then we need to divide it by the denominator that we calculated, which was the sum of all of these probabilities, not this one there though, which is 0.32. And now I can scale that guy, oh, a little too far there. I can scale that across to all the ones in this zone here. Alright. Now, let's get the rest of the probability. So I could go through and try and select all these, but I know that this probability adds up to 1. And I measure the probability of this zone, which is 0.32. So what I can really do is just go 1 minus 0.32. So it's 0.68 is the probability of this white region. So what that means I can do is I can take this guy and I can go take the probability, multiply it by 0.1, right? That's the probability that we're wrong, right? We're wrong about our measurement. And then we divide that by our denominator, which is 0.68. And now we can kind of scale that around here. It's a little tedious, but it is what it is. Now we're kind of noticing here, even though we had a a 90% probability that this is right, it still doesn't super increase our certainty, right? We're still at only 11%. We're only 1% sure that we'd be in one of these outside areas, or same with this area. I'm just going to type it in. So we're fairly certain that we're here, but that's actually still pretty a low probability. So we still don't have too much information. And now let's say this. We try and move, and we detect that we've crashed into a wall. We try and move in a direction, and we detect that we've crashed into a wall. So that actually seems kind of crazy here, that we tried to move, but we crashed into a wall, right? We should be able to at least move one unit, but we'll say we crashed into a wall the one we tried to move. So we'll say crashed into wall, and let's say the probability of our crash detection being right is 75%. So sometimes we've got like a crappy switch. This is kind of an inflated situation, but we say you got a crappy switch where it's 75% chance that your switch is reading right, 25% chance that it's reading wrong. So let's see how that applies here. So if we crash into a wall, that means we could be here, 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 or here, right? We crash into a wall, so we could be in any of these spaces. And I said that the probability of this being true or right is 75%. So that means the rest of this is 25%, or 0.25. All right. So now we can just go through and scale this and see where that puts us. This is kind of an interesting situation. So let's see here. First, we need to calculate our denominator for this zone. So that's here, 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 and here. For those of you that don't know, I'm holding down the control button to select multiple things. So it looks like that's 0.09. 0.09 is our denominator there. So what we'll do is this times our probability of 0.75 divided by our denominator, which is 0.09. And there we go. We'll scale this around. And drag that down. All right, and now let's calculate things. Calculate for the rest here. So, our denominator is 0.09. So that means we can find out the summation of the rest of this. I could either drag over it to find it, or I could take 1 minus 0.09, which is 0.91. 0.91. So we'll take equals the previous probability times the probability of this event, in which case event not being true, which is 0.25, divided by 0.91. And we can scale this that way and scale it that way. So what does that do for us? Well, it looks like it decreases our certainty of where we might be in a way, right? We're I wish this box would get out of the way. We were pretty, right, what happened is we kind of got conflicting information. And normally this isn't going to happen, right? You're going to get information that's really only going to help you. But what this means is we had something that said, hey, we should be able to move forward, but then we did move forward, and we crashed into a wall, unexpectedly, kind of. So that means it's likely that one of these things was wrong. But you can kind of see here's our position. And let's say we're a little confused, and our robot has a GPS measurement, and GPS is only so accurate, and so it can be made more accurate by interpolating like your current velocity and stuff like that. But let's just say we have a straight up thing that tells you within 1 unit of where it's at. So it's a 100% certainty that you are within 1 unit of where it tells you. And we're going to say that it thinks you're right here. So that means for this last one we're going to look at here, GPS reads 5.5, right? We're at 5.5, and so there's a 100% chance that it thinks that you could be there or 1 unit away, right? It's kind of actually a uniform distribution. And so we know, in this case, we know it's impossible to be here or above it, right? So it has to be here, here, or here. I consider this to be 2 units, right? Because it's not quite adjacent. So only you would have to make 2 steps to get there is kind of the way I think of it. It's actually called the Manhattan distance. But anyway, so we know that we are here in one of these 3 zones. So what that means is we have a 0.33, 0.33, 0.33, right? Really, it's 0.33 repeating, but it's because we took our, we assume that this is a uniform distribution, and so that means our probability of 1 is distributed across these 3 points. So that's kind of what we're left with here is the rest. Well, so let's highlight this guy and highlight this guy. So notice that it's not necessary for the whole zone. I mean, it is going to be 0.33 for each one, but I don't say this is 100%. I don't say this is 100%. It is true that it's 100% certain that we're in this area. Well, actually, no, that is right. It's 100% certain that we are in this area, and our Bayes rule will distribute that out. So 100%. Sorry, that was something I was doing incorrect, right? This is the correct approach. We're saying 100% certain that we are in these 3 spots, so that means a 0% certainty that we're there. So I'm only going to do these 3 cells here and figure out what that changes our probability, because we know the rest of them are going to be 0 because they're going to get multiplied by 0. So let's find our sum here. It looks like it's 0.15 if I just kind of do that in my head. So that's our denominator. So we're going to do this cell times 1 divided by 0.15. Alright, and I was doing a little bit of stuff in math in my head to actually get to this point before. It's something you got to be a little careful of. And so that means the rest of this turns out to be 0. So I'm going to just kind of scale this as far as I can get. All right. And yeah, so we've got a pretty high certainty now that GPS kind of gives us really high certainty of where we might be. Probably would have been a better idea to check our GPS first, but we've really increased our certainty. Now, if this wasn't 100% certain that we were in one of these zones, that would obviously kind of maybe have like a normal distribution that would bounce out and say that, okay, we still have a probability kind of being here, etc., etc. But that's just kind of what I came up with on the fly. So this is applying Bayes' theorem without really doing the math in a formal fashion, but kind of thinking about how you might apply this in a kind of discrete fashion, meaning that we've got things split up into cells. If you want to try and do it in a continuous fashion, that's a much different situation, but this is a good way to kind of start approaching the problem to understand it.